All right, then. Let's get started for today. We were talking about deep networks in face recognition of identity. And we described one of the networks. So you have the paper in Canvas. And we said that usually for training, people like to use the cross-entropy loss, right? So let's very quickly see what this cross-entropy loss is, because you will see this used not only in face recognition, but object recognition and other high-level computer vision tasks that we will describe next week, okay? All right, so in order to introduce the cross-entropy loss, I'm just going to give first a description of entropy and cross-entropy, and then that will allow us to define the cross-entropy loss, all right? Okay. Now, obviously, the cross-entropy loss, it's derived, as you may know, from Claude Shannon's classical paper where he introduced information theory, right? Famous paper. It's one of those papers that starts a whole new area of research, right? Shannon's idea, the original idea, was to model and measure the flow of information between a sender and a receiver, right? So that's a basic a basic premise of the paper. For Shannon, the sending a bit of information was equal to reducing uncertainty by a factor of 2. Why by a factor of 2? Because a bit is either 0 or 1. It's binary, right? So it's a factor of 2. So for example, let's say that you want to model the weather, right? That's a classical example that it's given in signal processing when they introduced this topic. So imagine that you live in a world where it can only be either sunny or raining, right? There's no other possible states, right? So when you open your weather app in your phone, right, which we probably do every day, right? We open the weather, and it's only going to say, is it sunny or is it raining, right? That's all we can say. Now, let's say, for example, right, this is just an example. Let's say that the probability in Columbus, right, where we live, of being sunny is equal to 0.5, right? So 50% chance. And the probability that it's raining, it's also 0.5. Okay? Make sense? So 50-50. And we don't know. And every day we wake up, we open the weather app, and it says, is it going to rain, or is it raining, or is it sunny, right? Now, when they tell you this, the sender, in that case, the sender is your weather app, right? Sends you 1 bit of useful information, right? So if I tell you whether is sunny or raining, right? Let me say sunny or raining, S or R. Then I am sending you 1 bit of useful information, okay? And I want to emphasize the word useful here, and that's the key that I'm going to try to describe in the next few minutes, right? Useful information. Now, what I say useful, why do I say useful? Because your weather app, maybe it's just displaying a 0 or a 1, right? Telling you 0 for rain, 1 for sunny, right? And that's it, right? It's 1 bit, and it's sending you 1 bit of information. You see 1 bit. Or maybe it's showing you a very nice graphic of a scene with a sun and a landscape, or a scene with heavy rain, right? Now, to construct that, to send you that image, the weather app is using a lot of bits, right? Maybe hundreds, thousands of bits. It doesn't matter how many bits they send you. They only send you 1 useful bit of information, because you're only reducing uncertainty by a factor of 2. Right? You have 2 options, and they're telling you which of these 2. So that's what we mean by useful. All right. If the number of possible weather conditions, though, is much larger, right? So let's say in my example number 2, maybe I have, say, 8 possible states, right? So in that case, i.e., I would have 2 to the power of 3, right? 8. Then in that case, the weather app sends you 3 bits of useful information, right? Because it's 2 to the power of 3. You see how this works? And so on and so forth, right? So in general, if you have 2 to the power of p possible states, then the weather app is sending you p bits of useful information. Okay. So let me say that in general, if the number of states is, what do I use here? P, n. Then the number of bits, right? The number of useful bits is the log 2 of n, right? Yes? Okay. Now, of course, this result is only follows if the probability for each state is exactly the same, right? 1 over the number of possible states. In the more general case, then that result needs to be amended. So for example, I could have here that previous example that I had, I could have another case such that the probability of sunny in Columbus it's 0.75 and of rain is 0.25, right? Well, maybe I should have done the other way around if it's Columbus. Probability of rain in Columbus, it's 0.75 and sunny. And that's being optimistic. So what happens if this is the new estimate or the new probability model? Now, in this case, if the app tells you that it is going to rain, then the uncertainty has been reduced by a factor of, okay, so let's see that. The uncertainty, right? So if I learn that it's going to rain, or that it's raining, then the uncertainty, right? The uncertainty, or the uncertainty reduction, I should say, because obviously, is proportional to or equal, I can actually write equal, 1 over the probability of that state, right? The probability of, let's say, that state I, right? So in that case, I is rain, right? Okay, so raining. So in our case, that would be equal to 1 over 0.25, which is equal to 4, right? So when I am told in this model that the probability is 0.75 for rain, 0.25, then if they tell me it's raining, they've reduced my uncertainty by a huge margin. Why? Because my prior assumption is that it's going to be sunny, right? Because most likely it's going to be sunny. So when it's raining, actually I learn a lot, right? It reduces my uncertainty a lot. However, if it's sunny, right? So I open my app and it tells me it's sunny today, then the probability, right? The uncertainty reduction, then it's 1 over 75, and I want to take the log of that to know, oh, I'm sorry, I didn't do that here. So for this case, the number of bits is what we said before, right? The log 2 of 4, which is 2, right? Yep. Forgot to do that last step, right? Correct? That's what we had said, right? And in this case, it's going to be the log of 1 over 0.75, which is the same as the negative log of 0.75, right? Obviously. And this is equal to 0.41 bits, right? So in the first case, because I reduce uncertainty by 4, this is the same as sending me 2 bits, right? Because I reduced by 4, so 2 to the 2 is 4, right? So they are sending me 2 bits of information. But if they tell me that it's sunny, they only send me 0.41 bits of useful information, right? And that's because, well, the probability that it's going to be sunny is very high, right? Okay. Now, on average, right, we can compute the average of this. On average, I'm going to have 0.75 times 0.41, right? This is the probability that it's sunny times the bits that they send me. So 75% of the time, they're going to send me 0.41 bits, plus 25% of the time, they're going to send me 2 bits, right? Yep. And if we compute this gives me 0.81 bits of information, right, of useful information. So in that case, even if they just tell me that it's sunny or rainy with 1 bit, with a 1 or a 0, right, they're sending me 1 bit of information, but only 0.81 is useful information, right? All right. And this result here, right, this is what we called entropy, right? So this result here, this is our entropy. So entropy, we can write it down as, usually it's written as H of our model P, right, our probabilistic model. It's negative the sum over all our states I of the probability of the state I times the log on base 2 of the probability, right? Yep. So that's what you have learned in signal processing and probability theory, what entropy is. Now, to define cross-entropy, you are interested in the message length rather than the entropy itself, and the message length that is needed for me to send you to give you that amount of useful information, right? So let's see how this would work. To do that, let's consider a problem which we have modeled with 8 states, right? Say it's 2 to the 3, 8 states. And let me write the states as S1, 2, 3, 4, 5, 6, 7, and 8. Okay? These are my 8 possible states, S1 through S8. Now, I need to code these 8 states. I can do that with 2 bits, right? So 2 bits. So for example, I could do 0, 0. You agree? 0, 1, 1, 0. I'm sorry, 2 bits. I'm funny. 3 bits. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? Yeah? You agree? So it's one possible way of sending you the information of those states. Now, if all the probabilities for every state were identical, that is a really good way to code this. Right? We've already shown that. When the probabilities for every state are identical, then use this coding. But when they are not identical, then it depends, right? I could use some other coding. So for example, I could send you 0, 0 to indicate S1, because maybe S1 and S2, let's say, are very highly probable. Then I want to use as fewer bits as possible, right? Because otherwise I'm going to end up with this problem here, right? So maybe I'm going to use 0, 0 and 0, 1, right? That's it. So if my code starts with a 0, I know it's either S1 or S2, right? And then it can only be 0, 0, 0, 1. Now, if not, I'm going to have 1 as the first digit. Then I can have 0, 0, so 3 bits for 3, S3. 1, 0, 1. Then I'm going to have, let's see, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, right? So this is just another possible way of sending you the information. Now let's see where this would be a good idea and where this would not be a good idea, right? So let's say probability model 1 here. And let's say that the probabilities of our probability model, the reason why we have actually done it this way, is that the first one has probability 35.35, second one also 35, the third 0.1. I'm just going to write 10, so they all have 2 digits, but that's 0.1, right? Fourth 0.1, next one 0.04, 0.04, and the last two 0.01 for both of them, okay? So these are the probabilities of each of these 8 states. So far, so good? Okay, excellent. So now let's do the computations, right? So I have here, I'm going to do, so let me do it here. You may not see it well. I have, let's see, 0.35 times, how many bits do I use to send this? 2, right? So times 2 plus the next one is also 0.35, right? And 2, right? So 35 times 2 bits. What's the next one? The next one is 0.1 times how many bits? 3, right? Very good. So 0.1 times 3, 0.1 times 3. What else? And then I go to, what's the next one? 0.04 times 4 plus 0.04 times 4. And the last one is 0.01 times 5 plus 0.01 times 5, right? And if we multiply and add this, it gives me 2.42 bits. Okay? Now, what this means is that if I use this coding, every time I send you information, on average, rather not every time, on average, when I send you this information, on average, I'm going to send you a length of 2.42 bits over time, right? Yes, you see that? Because 35% of the time, I'm going to send you 2 bits. 35% of the time, I'm also going to send you 2 bits. 10% of the time, I'm going to send you 3, and so on, right? So on average, I'm going to send you 2.42. Okay. Now, what? You have a question? Yeah, go ahead.
Plus should be 5 rather than
4, it's 5, right? It's not? Oh, yeah, it's 4. I'm sorry. I thought I had done 5. Yeah, thank you. Good. Does this make sense? Yeah. Okay. I don't know why I did it the other way, but anyways. Okay. So the other one, probability model number 2, what would happen? What happens if the probabilities were instead, say, 0.01 for the first one, 0.01 for the second, 0.04, 0.04, 0.1, 0.1, and 0.35 for the last two. Okay? What would happen in that case? Then I would have 0.1 times 2 plus 0.1 times 2 plus 0.4, 0.4, 0.1, and 0.1. First one. 0.01, 0.01, 0.04 times 3, 0.04 times 3, and what else? 0.1 times 4, 0.1 times 4, 0.35 times 4, I assume 0.35 times 4, right? And I don't know if I did the calculations with 4 or 5, but my calculations was 4.58 beats on average, right? Now, you see that's the important difference, right? If this is a probability model, then on average, I'm going to be sending you 2.42 beats, actually sending you, right, with my coding. But if I use this other coding, I'm going to be sending you 4.58 beats, right? So depending on how I code my states, I'm going to send you a more or less information. Now, if I were to compute here the amount of useful information, right, using that equation, this is the entropy equation. Let's use that entropy equation to see how much useful information or how much entropy I have. So my HP for the first model, right, maybe P sub 1 to indicate the first model, this is going to be 0.35 times the log base 2 of 35 plus 0.35 the log of 35 and so on, all the way to the last one. This is going to be 0.01 times the log of 0.01, right? Yes? And if you compute this, you're going to get 2.23 beats, right? So the entropy, or on average, we're going to receive 2.23 beats of useful information. Okay? Now, cross-entropy is the difference between the useful information I receive versus what I actually send, right, or is sent to me. Now, obviously, if I send on average 2.42 and I'm sending 2.23 actual bits of useful information, well, this is a very good coding, right? Because I'm wasting very few amount of extra information. But if I'm using this different binary coding, then this is a lot of loss in my, or a lot of redundancy in my way of sending you that information. So we can write this result as the cross-entropy of HPQ, which is going to be equal to negative the sum of my PIs times the log of Q, oh, not PI, of QI now, right? Because that's a cross-entropy. And what that means is that the probability of this occurring and the log of the amount of information that, of bits, the probability of sending so many bits, right? So, which is that equation, right? This is this equation that I've used here, right? And this result obviously is the cross entropy. Okay. All right, good. So if you want, you can write it as P is the true, maybe you can say underlying, if you don't know what it is, distribution, right? And Q is your estimate of the distribution, right? And now you see from this cross-entropy equation that the closer you are to the true underlying distribution, the smaller the cross-entropy is going to be, right? Now, when P, so when P is equal to, or I should say Q equal to P, that'd be better, right? So when my estimate is exactly the true model, then the cross entropy of PQ is actually equal to the entropy, right? And when they are different, then this cross entropy is going to be larger than my entropy, right? So subtracting the entropy from the cross entropy tells me how far away I am from my goal, right? Now, if you want to do that, right, let's say that I want to write now here how far away I am from this. So all I need to do is write this down, move this here. So if I want to write down the cross entropy minus the entropy, right? That tells me how far away I am from estimating the true underlying distribution model, right? Or the probability model. And this has a, this is called, anyone knows how this is called? Anyone? What's that? That's correct. That's a KL divergence, right? Okay, so let's use this to derive our loss function. So remember that we have images of faces. We have a deep neural network that has a certain number of layers. Usually, remember, you do convolution, max pooling, convolution, max pooling, and then something else, maybe some fully connected layers at the end. You are going to usually use the ReLU nonlinear function, activation function in each node for the layers, right? ReLU, remember, is 0. So ReLU of x, it's equal to 0 if x is smaller than 0, and it's equal to x if it's larger or equal than 0, right? Okay, so in our deep neural network, what we're going to have is now we want to train this network. So I have images of faces, right, like this. This is an image of a face, and I have many images like this, right? Right, so I have many images. This is my, remember, my set, my training set X. I fit this into my deep neural network, which is given by a directed acyclic graph, obviously. And then I have at the end the last layer is a certain number of nodes, say from P1 all the way to P capital C, okay? So the last layer has capital C nodes for the C classes that I have, right? So in that case, if I have C different identities. Make sense? Yep. Okay. All right. So P1 basically here computes the probability. So this is the probability of identifying person number 1, and this one the probability of person number capital C. Okay. Now we want to define the cross-entropy loss. And for that, we want to use the equation that we have derived over there, which is h of pq. It's equal to the sum of I, my pi's, the log of 2 of qi, right? So remember that a deep neural network is nothing else than a functional mapping, right? So it's estimating my functional mapping f of x. So this is xi, right? This I have xi, and this is my yi, my output. So this deep neural network is estimating this output yi, right? And I want if the probability model that I have here, right? This one that I have here, these probabilities are very close to the true ones, right? This is going to be as small as it can be, right? Which is the entropy, right? That's as small as it can ever get, or as small as it can ever get, right? Okay, so this is the cross-entropy loss. Now, usually, for these deep neural networks, people will use this equation, but they will either use the natural log or the log base 10 or base e, right? So the natural log, most typically, so I can probably write it as ln or just the log. And the reason for this is because people started doing this and they just kept doing it, right? The reason, whoops, sorry. The reason you can do that is because the log in any base, right, can be defined as the log of base 10, right? By just dividing the result of the log by the log of the base, right? So, you know, it's just a mapping from one to the other, so it doesn't affect the results. So the reason this works, right, or the way this works rather, is by forcing this distribution, right, that you're estimating here at the end to be as close as possible to the true underlying distribution, right? Because when they are identical, this function is minimized, right? So this is a way of minimizing a loss function that forces you to estimate the true underlying distribution of your data. Very common, very popular in deep neural networks. Okay, any questions before we move on? Nope. All right. Great. So very briefly, I want to talk about phase databases, the construction, and as I already said in a previous lecture, the construction, curation, and maintenance of databases in computer vision is one of the most fundamental problems or topics in the area. Unfortunately, for many years, this was thought not to be very relevant. because people said, well, you just take some pictures and you're done, right? There's much more to that than just taking some pictures, right? Creating good data sets is a very complicated, very very expensive process. And no research area, computer vision is not the exception, no research area can survive without really good, well-curated data sets, okay? So the reason computer vision data sets are now very important and people make even careers out of this is because a group of us started many years ago in the late 90s, early 2000s to create data sets for faces, because that was the problem back then in research. And some of those became really popular, very famous, and that is what allowed computer vision algorithms for face recognition to advance so fast, so much so that now you have computer vision systems in many, many different applications out there, right? From your cell phone to your social media to many other things. Now, there is a privacy concern with face recognition systems as they have occurred. I would have liked to do a lecture on ethics. Unfortunately, we're running out of time and we still have a lot of things to cover. So I doubt I'm going to have time to talk about this. However, on Tuesday, Matthew Turk, Professor Matthew Turk, who is now the president of the Toyota Technological Institute at Chicago, he is going to be, remember, he's the guy that invented eigenfaces. He is going to give a talk here in the department, which I strongly encourage you to attend. I promise a really nice, interesting talk, and he's specifically going to talk about the ethics of many of these computer vision algorithms that we're developing. This is of huge concern to the community right now, so please, if you can, do attend, because this is a fundamental topic that I really like to talk about, and unfortunately, gonna run out of time. Okay, so face databases. Let's cover this very quickly. I'm just gonna give you some quick overview, and then I have one more topic on faces that I want to cover today, and then next week we're going to go back to object recognition, which at this point you're going to see that after we learn how to do that for faces, we basically learn how to do that for any other object, right? Object categorization and object recognition, and I'll talk about those, which are just basically I wouldn't say trivial, but just extensions, not so complicated extensions of everything that we've done here. And then I want to talk about some other high-level vision problems also next week. And then after that, we are almost going to be done, so we'll see. We'll have one final lecture on some of the many other topics that I could cover. Okay, so databases. So in the 1990s, before the late 1990s, I should say. Oh, question.
Going back to the cross-entropy loss here, for your PI, which is the true distribution.
Oh, yeah, I wrote here, yeah, you're right. This should be the true and the estimated. So this could be Q1, QC, right? Right.
But when you have it labeled, you would just label it as this is this certain person, right? So you don't.
So here's what's going to happen, right? So yeah, let me change the notation here because that's just not right. Hopefully that's going to clarify. So this is going to be the true one, which is PI, right? And this PI is going to be PI1 through PI capital C, right? And these are going to be zeros everywhere except the 1 for the identity that this image corresponds to, right? And that's your ground truth data. This is, remember, your training data, right? From 1 to, oops, not C, capital N or small n, whatever, right? Okay, makes sense? So this is your training data that you're going to use to backpropagate, right? And then the estimates that you're getting here are your Qs, right? So Q1, through, actually, yeah, QC, right? So now you're going to have here, you're going to do the sum over I and j of ij and qj, right? Make sense? Oh, there will be ij as well, of course. Oops. Ij, because for this I input, I'm going to get here Q I1 to IC. Yeah, that makes more sense. Does this clarify? Is that better?
Yeah. So each time you pass it in, you want basically the probability that it's a certain identity.
So, well, this is going to be, since these probabilities, all of these are going to be numbers between 0 and 1, right? But the sum of all of them is going to be equal to 1, right? Because all the probabilities can only add to 1, right? So if you use the softmax, that's why you have the softmax, remember? The k-way or c-way here, softmax function. This is what the softmax is going to do. So you remember, in the denominator, you have the sum of all the probabilities. That's just to normalize the sum to 1, right? And so that output with a softmax is going to give you a probability. This is a real number between 0 and 1. Okay? Now, that may be 0.1, 0.1, 0.2, 0.3, 0.7, whatever it is, right, et cetera, right? But they all have to sum up to 1. And then this is a true one, right? But the true is binary. The truth is you're either A or you're not. It cannot be anything else. So the point is to modify these real numbers as close to all zeros except for 1 that's going to be as close to 1 as possible, right? And if you could do that, then that's going to be minimized, that cross entropy here. Okay? Any more questions? Sorry about the mess on the final notation, but you're right. I should have done it this way. So going back to data sets, in the 80s and 90s, there were some very tiny data sets. So there was a professor here actually at Ohio State in our department in EC that in the late 60s or early 70s, he created a data set of side views of faces where you could basically just see black and white, right? So at that time, cameras were so bad, they would just convert everything into binary images. And then you take the silhouette, right, the shape of the side view to try to do recognition with shape-based methods, right? But as we've seen then in the late 90s when Matthew Turk and others started working on the shading-based models from data, like eigenfaces, then more data was needed, right? And there were, at the time, 2 data sets that became very, very, very popular. The first one was the Ferret data set. The Ferret data set was created at NIST by Jonathan Phillips. And Jonathan just created a large data set and a competition also to participate on, to see how well algorithms could do on performing on these data sets. This database included 1,199 identities. And image were taking over 15 sessions in a lab, right? So he installed illumination, camera in a room, and then over many, many months, he brought in people, the same people over and over again, and took pictures of the same people, right? And then we developed later on what we called recognition of duplicates. By duplicates is meant, if you read this in the literature, that you train your system with data from, say, session 1, 2, and 3, and you test it with sessions 4, 5, 6, and 7, right? Which means that these images are of the same individuals, usually under the same illumination, pose, expression conditions, but taken a much later time, right? So there is this effect that the person has changed over time. So that was one of the very famous data sets. And the other one was the AR phase database, right? And this was also collected in the lab. And this data set includes images of, oops, I don't have that here, of a smaller number of individuals, but it included images under multiple illuminations, multi-illumination conditions, partial occlusions, and the way it includes partial occlusions is by people wearing scarves or sunglasses, so that they're actually occluders that make face recognition difficult, and expressions. And with that, the new areas in face recognition of recognition under partial occlusion that had never been tackled before, and expression invariance, expression invariant face recognition, that these two topics I've already talked about. The reason they exist is because this data set actually introduced these images, right? People didn't try to solve this problem before, not because the problem was not interesting, because there was no data to even think about solving that problem. So these two data sets became very popular in the late 90s, early 2000s. And then by the late 2000s, these data sets were becoming obsolete, mainly for two reasons. The number one, these data sets were relatively small. For the time, they were very large for the time. I mean, I remember back then there were very few computers that could store this data for long, right? Because the storage back then was pretty bad, believe it or not. But the other problem that we had was that these images had been collected in the lab, right? And when you collect images in the lab, what happens is that you end up with images that are much, much easier to work with than the images that you collect outside the lab, okay? Now, outside the lab, this is usually called in the wild. And that's a term, I'm going to put this in quotation marks, that's a term that comes from biology, because in biology, when you start studying things outside the lab, what do? You go in the wild, right? In the wild, and you actually study biological specimens in the real world. So computer vision adopted that wording from biology, and the labeled faces in the wild database, LFW for short, was created in the late 2000s, mid to late 2000s. And the way this was built was by going online, any search engine, and start downloading images from the internet. And the data set that they ended up constructing at the time included 5,749 identities, of which 1,680 identities had 2 or more images per identity. Okay? Now, at the same time that this was going on, this became a very popular data set in the late 2000s, early 2010s. That's what people used. But at the same time that this was happening, Jonathan Phillips, who had created that FRED data set, and as I said, this FRED data set had a competition back in the day that you could participate. Very few people participated at the time because the algorithms were so poor or performed so poorly. in even simplistic data sets like these. But then in the 2000s, he created the face recognition grand challenge. I think it was FRGC, I assume. Do I have this here? Yeah. Also organized by NIST, obviously. And there was a massive data set, mostly of data collected at the University of Notre Dame by Kevin Boyer and others. And what they did, again, recognition of duplicates. Now, this was filmed by the researchers themselves. It was not downloaded from the internet, but it was filmed outdoors in a less constrained environment than in the lab, but still a relatively in lab kind of conditions data set, okay? And that competition went on for years. And at this time, with these two new data sets, algorithms kept improving, right? And they started to getting in the early 2010s, really getting to really good accuracies, right? To achieving really nice accuracies. Most recently, then, we have had a number of extensions of these data sets. One of them, there are many, but one of them that I'm going to mention that has been published recently. It's called Megaphase. And Megaphase is a set of 1 million images. 1 million images. It includes more than 690,000 identities. Okay. And the reason experiments like the Megaphase were constructed with more images is because these data sets, remember, were created because the algorithms could basically solve these problems at the time in the mid-late 2000s. So we needed more data sets, so these were created. And when algorithms were saturating on this, meaning the accuracy were really good, then people started testing with large data sets. Now, you see that the number of identities are almost identical to the number of images, and that's because obviously annotating 1 million images is not the easiest thing, especially for identity. We tend to think that we're very good at recognizing identity. We are not, right? So the way to address this is by computing what's called face verification, and instead of face recognition, in place of, or in lieu of face recognition. And face verification means that I tell the system who I am, the system looks at my face, and determines whether I'm telling the truth or not, right? So this is a binary classification, true or false. That's it, right? It's a much easier task than face identification, where I have to tell you who you are from a single image of maybe potentially hundreds of thousands or millions of people out there. Now, for this, remember that one of the best ways to display the results is with an ROC curve, right? That we have seen. And if you plot an ROC curve with false positive, false negative, right, recall, and sensitivity, and so on, then the accuracy results of the best algorithms, or let's say of many algorithms, the ROC curves look something like this, which I find actually interesting that they publish this, because obviously that curve is impossible. Because remember, nothing can be under that curve of 50-50. That's absurd. But the best results that they tested, the best networks in that case, that they tested, deep neural networks, were between 0.6 and 0.8 here, and they look something like this, right? Something like this. You have that exact curve in the paper they posted online, obviously, the Megaphase paper. And that's where we are right now, right? We are testing algorithms in face recognition that can do recognition in hundreds of thousands of identities, right? Okay. Now, any questions about this? The final topic I want to cover very briefly is recognition of facial expressions. Okay? And in particular, we're going to focus a little more about facial expressions of emotion, but I want to talk mostly about facial expressions in general. So now we have talked about recognition. So first, face detection, how we detect faces. Second, face identification, how we identify, how we recognize the identity of people. And the last one is how we recognize expressions, right? What you are expressing in your face. So let's do that. Okay. So recognition of facial expressions. Now, question.
What kind of accuracies were algorithms saturating at first?
So this is a very difficult question to answer because I used to criticize my community for creating so many data sets because it created the false impression that we were solving the problem, right? So remember when I talk about sequestered data? Remember what that was, right? So that someone keeps some data sequestered. That was the case in FRED, that was the case in FG, the Face Recognition Grand Challenge, FRGC. But it was not the case for the other data sets, right? And the problem is that you eventually saturate because you have access to your testing data. And if you have access to your testing data, what's going to happen is you're going to keep modifying your algorithm until it works on your testing data. And that's a weird way of saying it saturates. It saturates because I know what my testing data is, right? So that's absolutely absurd. In fact, it was so ridiculous that for years, you could see if I could plot time here in the x-axis and accuracy, right? The recognition or classification accuracy. Now, let's say that I had a new data set that appears, say, the AR data set at time 0, okay? And then accuracy would grow quite rapidly and then maybe slowly, and then it would saturate, right? Oops, sorry. And then it would saturate, maybe close to 100%, right? Right here, okay? And then when this would happen, a new data set would appear right here, right? At this other time, T1. And then the same algorithms that were saturating in accuracy on this data set would go down maybe here, 20, 30%, right? And then you'd see the same trend. It would increase like this. And then another data set would come up at time 2. And then it would go down back again, right? And it kept doing this, and at some point, I kept saying to my friends, to my colleagues, we're not learning anything. We're not building good algorithms, because every time a new data set appears, we're back to where we were, which is designing algorithms that work specifically for that target data set, right? I think that's still the case, unfortunately, for most problems in computer vision, right? So the hope is, which I think is a misplaced hope, but the hope is that if your data set is large enough, right, eventually it doesn't matter that you're saturating to that data set because that data set includes everything, right? But that's not true, is it? It doesn't matter how large your data set is. The data sets that you collect, especially most data sets, most modern data sets, which are collected through the internet, through search engines, right, web search engines, they are very specific narrow type of images, right? Or they include, rather, a very specific narrow type of images, those that are uploaded in the internet, right? These are not all the normal images that you see on a daily basis, are they? So there is this famous example that I like to point to where Google had, and we'll talk about this next week, Google had a deep neural network with a specific architecture and loss function that worked really well on an object recognition data set, okay, that we'll discuss next week. And therefore, they decided that it had solved the problem of object recognition, and they decided to post this algorithm to make that algorithm available to the world on Google's website. And they posted it there, and first day, probably few hours after it was uploaded, a reporter from, I think it's the Washington Post or one of these newspapers, went online, uploaded the picture of an African American, and the algorithm said gorilla. Right? That's a very bad mistake. I mean, this is not, and chair would have been better, right? Like, yeah, okay, I mean, that was a terrible, terrible mistake. And why did that happen? Well, because the data set that they used to train the system did not include African American, or very few African Americans, if anyone, right? So the system never learned that. And that's because the way these data sets are constructed, are created, and that's the problem, that we're still feeding our models to these very, very artificial data sets. To say that it saturates, it means that it saturates for that specific data set, not even for the data sets that you could collect, right? So that very specific data set. So this is a general problem that I would have liked to talk more about in my ethics class, right? My final class that I had in mind, but unfortunately we're going to run out of time. But that's the typical dynamics that you see in the community, right? And that's happening in object recognition too, right? I mean, you see this kind of curve all the time. All right.
For those data sets, they were getting close to 99%.
I would say not necessarily 90. Well, it depends on which data set, but maybe it was 92, 94, right? But it gets to a point in these data sets that getting better than that, it's almost physically impossible. So humans, so in the face recognition grand challenge that then was converted most recently in the last few years, 4 or 5 years, to another competition that was actually a closed competition and only a few people could participate. But you had to have a lot of money in order to be able to participate in that because the difficulty of that data set was extraordinarily large, right? So only people that were funded by the government were participating, kind of a self-driving car type of funding, right? That you need millions, to build algorithms that can work with this large data set. And the way they tested these algorithms is they compare it to human performance, right? And they show that the best algorithms right now on that specific data set is actually better than human performance. Now, when I say that, I mean average human performance. There are a specific type of humans, there are called super recognizers that are extremely, amazingly good at recognizing identity through faces. No one knows why or how they do it. They don't know, right? They just do it. And I mean, it's the same way that you know how to speak English, right? You don't know how you do it. You just learned from, when you were a kid. That's it. It's the same way for them, right? They learn to recognize faces, and they don't know how they do it. If not, they could tell us, and we could implement that, but we don't know. But those people are still better than the best algorithms, right? But only those people. So in that regard, computer vision systems for specific data sets, very difficult data sets, are becoming as good as humans, if not better, right? Yeah, but, and object recognition is a whole different story, right? We'll get to that next week. All right, recognition of expressions. We're going to run out of time. So not surprisingly to you guys, humans communicate non-verbally, right? We communicate verbally, communicating verbally all the time, but I'm actually communicating non-verbally, right? I'm moving my arm, I'm making facial expressions, right? Like, oh, what happened? And these facial expressions are very useful to communicate with one another. That's why you prefer to video chat with someone versus speaking over the phone, right? So we want computer vision systems that are also able to do this recognition, right? And to do that, what we do, we analyze what's called the facial muscle articulation, right? So under our skin, we have a number of facial muscles, right? And when we contract these facial muscles, the skin wrinkles, and that creates a shading change that is perceivable from the outside. When that occurs, we call this an action unit. So that leads us to action units. And people just call them AUs for short. Okay, so for example, AU1 indicates that the inner corners of the eyebrows, are moving up. And that's because we have a frontalis muscle here that when you contract it medialis, meaning by the middle section, it raises the inner corners of the brows. AU2 is when you contract the same muscle, the frontalis muscle, but lateralis, in the lateral portion, and that raises the outer corners of the eyebrows. Okay? AU4, it's actually a set of muscles that contract the inner corners of the eyebrows. So the inner corners go inwards and a little downwards. Okay? AU12 stretches the mouth in what you would call the classical smile, and so on. Okay? So you see how this works. They're all numbered. Each action unit that is perceivable, and this is the key to understand action units, right? It's not every possible facial muscle articulation you can perform, are the facial muscle articulations that you can observe from the outside from a shading change on the in the image, right? So in computer vision, the goal is to recognize or identify these action units, right? Now, I want to emphasize that if you read about facial expressions of emotion, the goal must be the recognition of action units. It cannot be the recognition of emotion categories. Like, I want to recognize whether people are happy or sad. And I don't have time to talk about this. Maybe in the recitation, I will add some information on that online. But other than that, I just don't have the time here to go into the details. But let me just summarize it this way. Not everyone who is happy is smiling, and not everyone who smiles is happy, right? So if you want to make the inference that if I see you smiling, you are happy, you're going to make more mistakes than anything else, right? Because let me amend what I just said. Most people that smile are not happy, and most people that are happy don't smile, right? Otherwise, we would be smiling a lot more than we do, right? We just don't externalize it. So what that means is that what is important is to extract the facial muscle articulations, the action units. Once you recognize the action units, you can combine this with body pose, body motions, like hand motion, arm motion, dynamics, and contextual information. Okay, the context is very, 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 very important. And again, I'll add more information online on that. So we want to recognize action units. That's our goal. And the question is, how are we going to do that? So I'm going to summarize here very briefly. I'm going to give you an algorithm to do that, right? So the first thing I need to do is to define a face space. Right? This is the same process, by the way, that we use for face recognition of identity, right? Face recognition. Okay, the number one thing in our algorithm, as was the case for identity, is detect some landmark points. On the face, right? And by this I mean two-dimensional landmark points on the image, and we already know which algorithms we can use to do that, right? Now, if you allow for faces to be in any pose, maybe in your data set all the faces are frontal, then you don't have to do that. But if they're not all frontal, then you need to recover the 3D coordinates of each fiducial point, right? Each landmark. And then what we would call frontalize the image, right, of the face. And remember, we did that for identity when I talk about deep face, right, where you either map it to 3D mesh or you reconstruct it in 3D and then you rotate it with a rotation matrix and then you reconstruct it there. However you want to do it, there are multiple ways that we've seen, but you need to do that. Okay, so number 3, let's define these landmark points as Sij's. And this vector Sij is going to be Sij1 transpose. Sij1 is a vector through Sij transpose P transpose, where in this case each Sijk defines the UV coordinates of the image of that landmark point, right? So right down here. So let's see. So this is the vector of the of the jth landmark point in the ith image. I should say frontalized image because I assume that I have frontalized them already. And Sijk is equal to Uij and Vij, right? I'm sorry, K, which are the two-dimensional coordinates of the kth landmark point. I'm sure the jth landmark point, and P, right? P here is the total number of landmarks, right? Right? I think it should be. Okay. Now, once you have this, you can take your face, right? And in your face here, say it looks something like this, right? You're going to have many landmark points. Maybe this is one, this is another, here, 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 right? Something of that nature. Okay? Number of landmark points that you have detected. You can use any of the mid-level or low-level algorithms that we have defined. Maybe you could use even an active shape model to find those, right? And then once you have this, what we're going to do, we are going to create a delunary triangulation of this by creating all the triangles between these possible pair of points, right? So you divide this into some sort of triangulation. Right? And it's going to look something like this. You get the gist, right? And so once you have done this, again, this is the delunary triangulation. Once you have done this, you can construct your shape feature vector, right? So now my shape feature vector is going to be given as Xij equals And now, obviously, as you know, this is your modeling. So this is your decision to decide how you're going to define that feature vector, right? So for example, I could do dij12 all the way to dijp minus 1p theta 1 transpose theta p transpose, where these dij's, dijab, is the distance, the Euclidean distance, for example, between Sij and Sij-b, right? So the true norm, for example, of this or any other norm, right? So that's just the Euclidean distance, which is every pair of landmark points. And this theta A is equal to a vector of theta A1 through theta AP. And these are the angles between the different delunary triangles at landmark Sij, right? So note here that at each Sij, right? So for example, at this Sij here, I have this angle would be, so if this is Sij, this would be theta 1, theta 2 would be between these two here, theta 3, this one, theta 4, and so on, right? And if you could go all around that, this would be the 360 degrees total, right? If you add them up. In some cases, it's going to be a less because you cannot go all around it, right? Okay. So this is your shape feature vector. And in the same way that we define a shape feature vector, we can define a shading feature vector, right? So that we model both the shape and the shading. So let's see that very quickly. For shading, we are just going to write, for example, let Gij be equal to Gij1 transpose all the way to Ij P transpose for the P landmarks, where now my Gij transpose is a vector of the outputs or results of convolving that convolving a window around the ijth, the pth landmark point, right? The k landmark point, convolving a window around that point or center at that point with some Gabor filters, for example, right? So output of some linear filtering, right? As we saw in 5460, linear filtering, and here in detail when we talk about Gabors. And you could use Gabors or any of the other filters that we have introduced, or any other filter that you find appropriate, right? And that will describe the shading. And then finally, your feature vector, let's call it Zij, can be defined as my Xij that defines the shape, and the Gij that defines the shading, right? And that's my face space. That's how I actually defined my faces, right? And now that I have this represented in a feature space, I can use the same classification methods that I've introduced before, right, to do classification in that face space for action units. Now, the difference from before and now is that before it was the identity or a face, not a face for detection, and here it's does this image include action unit I in it, or does it not include action unit I? Okay. I'll very, very, very briefly go over this in our next lecture, though I wasn't planning to do that. I was hoping we could finish this. I'm going to go this probably in 5 minutes in the next lecture, and then we're going to go back to object recognition and then more high-level vision problems. All right? I'll see you next week.